Hey everybody, your Friendly Math Tutor here with our first lecture video. This one is going to focus on Unit 1 of the AP Calc test, which is limits and continuity. Make sure to check out our TikTok, Instagram, and Facebook, where we'll be posting videos all week that are related to limits and continuity. And also check out our Patreon, where we'll have worksheets and videos reviewing those worksheets. All right, so let's get started for today. So one of the first major things that we're going to have to do in this unit is to be able to read a graph and evaluate some limits. So if we take a look at this graph, our first limit says the limit as x approaches -3 of our function. So the first thing we're going to do is we're going to go over to -3, which is right here, and then we're going to go up or down until we get to the graph. So we go down to the graph till we get to this point. All right. First of all, the limit from the left and the right are meeting up at that point, and it's a solid point. So really there's no issues here. So all we have to do is look over, and that looks like a value of -2. So our limit is simply just going to be -2. All right. The second one, the limit as x approaches 1. So this little symbol right here means from the left. So we're looking at 1. And we want to see what happens as we approach it from the left. So we're going to pick a point maybe a little bit before 1 and see where the curve is there. And the curve is up here. So what you want to do is see what happens as you move closer to 1. You're moving along the curve this way, and you start to approach that hole. And that hole is at +1. So as the limit as x approaches 1 from the left, the y values are approaching +1. It doesn't really matter that there's a hole there because it's the limit as x approaches it, not really when x is there. So the answer to that is 1. Now it says the limit as x approaches 1 from the right. So what I would do is just maybe pick a point that's a little bit to the right of 1, go up to the curve, and that puts you here. But it's coming from the right, which means it's actually moving left towards 1. So it's moving towards this point, which is at 3. So the limit from the left along this piece is getting closer to 3. And then finally, this one asks us the limit as x approaches 1 of f of x, just the overall limit, or the two-sided limit. And that is going to be looking back at both of these answers. From the left is 1 and from the right is 3. They're two different values, right? So this limit, the overall limit, is what we say does not exist. Or you can just write DNE. All right, so that's just a way to look at the graph and answer some limit questions about that graph. All right, the next section we'll move on to is algebraic limits. So we want to be able to look at a limit and solve it algebraically without a graph. So the first thing I would do, if it's the limit as x approaches a numerical value, so in this one we have -3, this one we have 4, and this one we have 2. The first thing I would do is just direct substitution. So just substitute this number in. So -3 squared is 9, 9 minus 9 is 0. And over here, -3 squared is 9, 9 minus 3 is 6, 6 minus 6 is 0. All right. So what that means is we have a hole on the graph. All right. So the graph meets up at both ends because it's not a piecewise function. So it has no option of being at completely different values like we just saw in that last graph. In this one, what we have is definitely a hole because it's 0 over 0, and it's a single function. So it is going to meet up. So the idea is this x value is -3. There is going to be some y value that hole lives at. And that's our goal, is to find that y value. So what we're going to see is this is actually going to happen in all of these. And this is just 3 examples of just 3 different things that you could do algebraically. So the first one is factor and divide. So what this is the limit as x approaches -3. I can factor this top to x plus 3 times x minus 3. And the bottom I can factor to x plus 3, x minus 2. So the x plus 3's simplify, or they cancel out, divide to 1. Now I can plug in again. You can think of this as this cancellation kind of gets rid of the whole, and it makes it a continuous function again. So now what I have is a point there, and if I want to figure out what that point is, the y value of that point, I just plug in -3 a second time. So if I do that, the limit is going to equal, well, -3 minus 3 is -6, and -3 minus 2 is -5, so our answer is 6/5. So we've got this whole of the original function that lives at the coordinate pair -3, 6/5. So the limit as x approaches -3 is the y values are going to approach 6/5. All right. And the next one, same thing. Plug in 4. 4 plus 5 is 9. Root 9 is 3. 3 minus 3 is 0. And 4 squared minus 16 is also 0. So we've also got another example here where we have a hole. So to find the y coordinate of that hole, so in this case, what I'm going to do, so our strategy is the factoring is not really going to work here. So you are going to multiply top and bottom by what's called the conjugate. All right. And the conjugate is root x plus 5 plus 3. All right, so we're going to multiply top and bottom by that. And what's going to happen is in the numerator of this one, this is just a difference of 2 squares. So all you have to do is the first and the last. So that becomes x plus 5, root x plus 5 times root x plus 5 is x plus 5 minus 3 times 3, which is 9. On the bottom now, I'm going to factor this to x plus 4 times x minus 4. And then I'm going to keep the conjugate there. There's really not much we can do with that. And what happens is x plus 5 minus 9 is really just x minus 4. And that x minus 4 will divide out with the x minus 4 on the bottom. Now again, that cancellation is kind of like plugging the hole. So now we can figure out where that hole was, because it's not a hole anymore in this simplified version. I do have a 1 on top though, so that's pretty important. Now I'm going to plug in 4. So I'm going to get 1 over 4 plus 4 is 8. And over here I get 4 plus 5 is 9. Root 9 is 3. 3 plus 3 is 6. So our final answer is 1/48. All right. If we take a look at our last problem, same idea. Plug in 2. Half minus a half is 0. 2 minus 2 is 0. This one is a complex fraction, so I think the easiest thing to do is just multiply everything by the LCD. So you can think of this thing as being over 1. The LCD between 1, 2, and x is 2x. So I'm going to multiply everything by 2x. And I get the limit as x approaches 2. 2x times 1 over x is just 2. 2x over 2 is just x. On the bottom, I get 2x times x minus 2. And now, again, we don't want to plug in a get yet because we haven't gotten rid of the hole. We haven't plugged the hole with anything. So we want a cancellation first, and that happens here. 2 minus x over x minus 2 is equal to -1. So now that we've canceled that out, we can now plug in 2. We plug in 2, we get -1 over 2 times 2 is 4. So the answer to that limit is -1/4. All right. So these are just 3 things that you can do when you get 0 over 0. I do realize that later in the course you'll learn L'Hopital's rule, but honestly, for this one, this is still probably the best way. Maybe not. But for right now, we're going through this course in order. So I realize a lot of you may have learned L'Hopital's rule, and you might be saying, oh, why is he not doing that? I'm trying to teach this in order, and this is just our first unit, and these are the ways that we can solve limits. There are, again, other ways, but these are the main ways that I think are most important: factoring and dividing, multiplying by the conjugate, and simplifying a complex fraction. All right. All right, let's move on to continuity part of this. So first of all, we're going to talk about the 3 main types of discontinuities, all right? The first one is an infinite. You want to just think of an infinite as a vertical asymptote. So this would be an example. So you got a vertical asymptote in a graph. whatever value that's at, we would say that there is an infinite discontinuity. Then the next type is a removable. So a removable is essentially going to be just a hole. So this is just like the last couple problems we were doing where they all had holes. They were all removable discontinuities. Basically, what makes it a removable is that it's almost as if you're taking a continuous function and you're just taking one point and just plucking it out, and it meets up on the left and right. So the limit would exist, but it would be what we would call a removable discontinuity. The last type is a jump. So a jump is going to result from like a piecewise function. So we saw this in our earlier example of when we were looking at the graphical limits. And when we have like a jump, that's something like this. So you literally have a hole just like this, but you have a complete jump. All right. So then I want to look at how we determine discontinuities, these types, from different algebraic problems. So let's say for our infinite discontinuity, an example would be something like this. So a vertical asymptote is going to be any value that you would divide by 0, but the numerator is not 0. If the numerator was also 0, it would mean we could use some algebra to cancel and simplify. So for this one, we can see that at x equals 5, right, it makes the numerator 15, but it makes the denominator 0. That is a vertical asymptote. So at x equals 5, we would have what's called an infinite discontinuity. For a removable discontinuity, one way you will see this is it will look just like this. So let's say we have x squared minus 9 over x minus 3. So at first glance, you say, okay, well, x can't equal 3, because if I divide by 0, then that's undefined. So it's definitely not continuous at 3, but which type is it? So if you only think of it as being, okay, well, whatever the denominator is 0, it's an infinite discontinuity, that would be incorrect. That works up here, but here, 3, when you plug it into the numerator, you get 0 over 0. So again, back to our limits from before, 0 over 0 will mean it's a hole. If it's a hole, then it'll be a removable discontinuity. And you can see why it's removable. You factor this top to x plus 3, x minus 3 over x minus 3. So the function in its current form, it has what we call a removable discontinuity at x equals 3. Well, the reason it's called removable is because I can quite easily remove it algebraically. I can just go like this. I've just removed it. If I create a new function and I just call it x plus 3, well, that doesn't have any discontinuities. That is just a continuous line. So you can't do that up here. There's no cancellation that's going to change it from a discontinuity to being continuous. But a removable is it's like super close. It's so close to being continuous, it's just not. So it's removable. So it's a different type than an infinite. You can plug this hole by canceling. You can't do anything. You have a vertical asymptote, that's just kind of, and just notice it's infinite. It literally goes on forever. All right. So it is important to understand the names and kind of like where they come from and why they are the way they are, and allows you to not just blindly memorize them, to kind of associate like where they come from and why they're called that. And the same thing with a jump. You quite literally, as you're traveling along the function, you're going to jump to another one. So a jump is going to occur when you have, let's say, a piecewise function. And what's going to happen here is when you take the limit as x approaches 3 from the left versus taking the limit as x approaches 3 from the right versus f of 3. All right, so When you are finding, for piecewise functions, continuity, you really want to find all three of these things. And those three things all have to be in conjunction with each other in order for it to be a continuous function. So we look at 3. 3 is what we would call our suspicious point, because something weird could happen here, because I'm just completely switching rules at 3. When I'm less than 3 and greater than 3, I'm doing different things. And if they don't meet up, then it's not going to work out. It's not going to be continuous. So when I plug the limit of 3, I just do direct substitution and I get 8. And then when I do the limit from the right, I pick this function because x is greater than or equal to 3. 3 minus 11 is negative 8. And then I take a look at f of 3. This is going to be important, and you'll see why. When I take a look at f of 3, I'm going to use this one again. So I'm going to get negative 8. All right. Well, these two being completely different just tells us that it's a jump, right? We're at 8, and then all of a sudden we're at negative 8. So we have to make this huge jump to do that. So this right here tells us that we have a jump discontinuity at, in this case, it's also at x equals 3. All right. If these were the same and this was different, then we would have another removable discontinuity, because the limit from the left and right will be meeting up, but there would be a different value. So that's why it is, in this case, it's not important, but in general, I say always find the limit from the left, limit from the right, and f of that value. And if they're all the same, then it's continuous. If the limits are different, then you got to jump. If the limits are the same, but the function at that value is different, then you're back to, it's a removable, but it looks a little different than this type of removable. All right, but it's still the same type. It'll be a different way that it comes about. All right, so they are the three main types of discontinuities that you have to be familiar with. All right. All right, let's take a look at another continuity example. So here's a typical problem that you'll see. You've got this piecewise functions and you have these constants a and b that are unknown, all right, for right now. And what we're going to do is we're going to try to find a and b that'll make this a continuous function. The first thing I would do is take a look at 1. 1 is our first suspicious point because we switch rules at 1, so we could have a jump happen there or a removable, and we're going to try to make that not happen. So we're going to take the limit as x approaches 1 from the left, the limit as x approaches 1 from the right, and f of 1. So 1 from the left is plugging 1 into this function, so that just gives us 2. 1 from the right is this function, so that gives us a plus b. And f of 1 is also this function, so it gives us a plus b. Some of this is going to seem redundant, but I just think it's a good habit to always do left, right, and f of that value for the times when you really do need it. But in this case, you get the same thing, so it's not going to be that useful. All right. So what this tells us is that a plus b has to equal 2 in order for that to be continuous. Well, there's a lot of values, right? There's an infinite number of values that a plus b could equal 2. So we need a little bit more information. So let's head to our second suspicious point, which is 2. So I'm going to do the same thing for 2. We're going to do the limit as x approaches 2 from the left, the limit as x approaches 2 from the right, and f of 2. Well, 2 from the left is just to the left of 2 would be this piece. So that's 2a plus b. 2 from the right is this piece. That's 6. F of 2 is also this piece, which is 6. Again, we get a repeat. Seems a bit redundant, but again, I just want to make sure that we're doing this correctly, because then there will be problems where that is important. All right. So this tells us that 2a plus b must equal 6. So we have a system of equations now. Well, I think the easiest way to do this, I would just subtract these. I'm going to subtract them this way. I know this is a little weird, but this is an AP Calc class, so I think that we know we can handle that. 2a minus a is a, b minus b is 0, and 6 minus 2 is 4. So a is 4, and if a is 4, 4 plus b is 2, so b must be negative 2. And we can double check that it works with this. 2 times 4 is 8. 8 minus 2 would be 6. So now when A is 4 and B is -2, you are going to get a continuous function because everything here and everything here is all going to work out nicely and we won't have any jumps or holes. All right, let's move on to infinite limits and limits at infinity. So infinite limits aren't going to be as easy to diagnose, where limits at infinity, well, I just see infinity or negative infinity, so my brain says, oh, that's a limit at infinity. But infinite limits are going to be disguised as just limits that we looked at before. So earlier in the video, we just did the limit as x goes to some number, and we said the first thing you want to do is plug that in, direct substitution. So if I do that, I get 4 plus 3, 12 plus 5 is 17. And 4 minus 4 is 0. This is different than what we got before. We talked about earlier in the class that 0 over 0 is a whole. 17 over 0, or any number other than 0 over 0, is not a whole. That's a vertical asymptote. All right, so that is really important that we understand that this might look like one of our algebraic limits from earlier, but it's really an infinite limit. And the reason we know it's an infinite limit, if you picture that at x equals 4, you have this vertical asymptote. So what you know is that, first of all, we have possibly different things happening on each side of it. So we've got to split it up into the limit as x approaches 4 from the left and the limit as x approaches 4 from the right. All right, and that, first of all, is different than how we solved it before when there was a hole. When there was a hole, we just did some algebra to simplify. But we're going to do this slightly differently, and you have to know why and when to do it differently. So this right here tells you when you see a number over 0, a number other than 0 over 0, it's a vertical asymptote. A vertical asymptote is going to have different behavior on each side of it, or possibly different behavior. So you want to split it up into two limits. Now, if I look at the limit from the left, well, what happens is, knowing that it's an asymptote, I have now narrowed down the infinite number of options to just 2. It either approaches the asymptote like this or like that. There's no other way to approach an asymptote. So what I'm going to do is, I'm going to imagine plugging in a number really, really close to 4, but to the left, to like 3.99999. And when I do that, since I only have 2 options, it either goes to infinity or negative infinity, I can do what's called sign analysis. If I plug in a number like 3.99999 and multiply by 3 and add 5, I know that it's a positive number. And if I take 3.99999 and I subtract 4, I know it's going to be a negative. And I also know that a positive divided by a negative is a negative. So since really close values to 4 on the left side of it, when I get negative values, it must be this option. It must be going to negative infinity. So that one-sided limit has an answer of negative infinity. Then I can do the same thing here. To the right, I know it's an asymptote. So I know I only have 2 options, all right? And this one I can say I know it's not that one. So now I'm at a 50-50 chance. I could guess, or I could just do a little bit of logical sign analysis, pick a number to the right of 4, so 4.00001. Again, 3 times that number plus 5 is going to be positive, but 4.00001 minus 4 is also positive. So since I always get positive values when I'm really close to 4, it must be this one. So it must be this one and not this one, so that goes to infinity. Then something that we did learn earlier is that also applies here is that when the limit from the left and the limit from the right are not the same, then the overall limit is what we would call DNE. All right, so a lot of times when you have vertical asymptotes, the overall limit's DNE. So many times it's possible. It's totally possible for them both to be going up or both to be going down. But a lot of times this is what happens. So since that's not that much fun, most of the time with vertical asymptotes, you'll be just asked a one-sided limit. All right. And this is how you do it. So to kind of recap really quickly, earlier we talked about how you plug in a number and then you do some algebra to simplify. That is when you get 0 over 0. When you get a number other than 0 over 0, that tells your brain, okay, this is a vertical asymptote. This could be only going to positive infinity or negative infinity. So I am going to just choose a sign analysis approach where I'm just saying, all right, a number just a little bit to the left or just a little bit to the right, is it going to produce a positive or a negative? And again, we know all of our positive and negative rules as far as division and multiplication, so we can do that pretty easily. All right, so that's infinite limits. Now we look at limits at infinity, which is very easy to diagnose. It literally just says the limit as x goes to infinity or limit as x goes to negative infinity. So the way that I'm going to show you to do this is to rewrite it like this. I'm going to divide every single piece of this, every term, by the largest power of x in the denominator. So that is x squared. So I'm going to divide everything by x squared. So x squared over x squared plus 3x over x squared plus 8 over x squared over 2x squared over x squared plus 4x over x squared minus 5 over x squared. And what that's going to give me is 1 plus 3 over x plus 8 over x squared over 2 plus 4 over x minus 5 over x squared. And the cool thing is, limits of constants are constants themselves. So this 1 over 2 is just going to stay there. And these 4 limits are all a number over a power of x. So if you imagine making the x infinitely large and doing, say, 3 divided by that number is going to be really, really, really small, and it's going to keep getting smaller as x gets bigger and bigger and bigger. All these limits are going to tend towards 0. So they're gone. So our answer is just 1 over 2. So I'm going to write that over here because we're going to do something similar here. So when you got infinite limits of rational functions, this is the general strategy. Just divide everything by the largest power of x on the bottom. So let's try that here in this problem. So I'm going to divide everything by x squared. So x over x squared plus 8 over x squared. This one is x squared over x squared plus 3x over x squared plus 7 over x squared. So we end up getting the limit as x goes to infinity of 1 over x plus 8 over x squared, 1 plus 3 over x plus 7 over x squared. All these limits go to 0, so we're going to have 0 over 1, which is just 0. Now you get some general rules that come out of this. What happens is, since the degrees are the same, you could just divide the leading coefficients. And here, since the degree of the denominator is bigger, you get 0. That's going to happen every time. But again, I don't know how, some teachers want you to show all that work. I at least wanted to show you kind of the actual way to go about that. All right. This one, we're going, also to say, these, since they're rational functions, which are just polynomials over polynomials, the limits towards negative infinity would have given us the exact same answers. But in this type, it might not be the case. So let's take a look at here. We're going to do the same thing. We're going to take the limit as x goes to negative infinity. We're going to divide everything by x squared. All right, and this one I'm just going to do it a little more quickly. So x cubed divided by x squared is just x. 3x squared divided by x squared is 3. And then I just get 9 over x squared. Then x squared over x squared is 1. And then I just get 7 over x squared. So here, those two are gone. They both go to 0. But we have an x. That hasn't happened yet. So when you have this leftover x, which is going to result when the numerator has a bigger degree than the denominator, then it's going to go towards one of the infinities. This is where you might get a different answer for positive infinity versus negative infinity. So what happens is the 1 and 3 are kind of now insignificant because 1 and 3 are pretty much nothing compared to infinity. So if you plug in, or you substitute negative infinity into x is negative infinity. So that is our final answer. Some might say that the limit just doesn't exist. That's a different type of does not exist. So I don't write DNE. I just actually write that it's negative infinity. And the other thing I want to talk about here is what these answers give us is the horizontal asymptotes. So this means that this function has a horizontal asymptote at a half, this function has a horizontal asymptote at 0, and this function does not have a horizontal asymptote, because as x gets infinitely large or infinitely small, the y value just also continues to grow without bound. All right? So these ones are a little trickier. You got to see what's left over. If that were like squared, then the negative squared would turn it into positive infinity, and you got to do a little bit more thinking if there's like coefficients. But that's the general strategy here, is to divide everything by the largest power of x in the denominator, and then kind of evaluate a bunch of limits that are either going to be constants or limits that tend towards 0. All right. All right, let's continue with a little bit more with infinite limits, or limits at infinity. So this is an example of where we would have to come up with our own limit based off of a question or something they wanted us to find. So if you want to find the horizontal asymptotes, that's when you have to do the limit as x goes to infinity of our function to find one asymptote, and then possibly do the limit as x goes to negative infinity to find the other asymptote, if there is another one. So I mentioned earlier that if it's a polynomial over polynomial, so just a general rational function, that the limits, the negative infinity and infinity, are going to be the same if they give you a numerical value, which would be a horizontal asymptote. But when you have something like e here, you tend to get different answers. So the way that I would solve this is going to be a little different than this. Here, I'm going to do what I did in the last type of problem, except I'm going to divide everything by e to the x. So I'm going to go through and divide everything by e to the x. So I'm going to get the limit as x goes to infinity of 2 minus 5 over e to the x, and then 3 plus 3 over e to the x. And what happens is, just like before, these limits are just going to go to 0, and I'm going to be left with 2/3. So 2/3, well, y equals 2/3 would be one of our horizontal asymptotes. Now let's see if we get a different one, because maybe when we go to the left, it goes towards a different value. Well, here it's a little bit easier, because when you go to negative infinity, these two, we have to really understand the graph of e to the x. E to the x in general, we should know, just looks like that. And when x goes to negative infinity, that just goes to 0. So there's really nothing to do here except realize that these two limits just go to 0, and these are constants. So this one is going to go to negative 5/3. So y equals negative 5 over 3 is the other horizontal asymptote. So I did this example just to kind of show you that the limit to infinity and negative infinity infinity and negative infinity, they don't always go to the same value. They will in a basic rational function, but when there's other types of functions, these transcendental functions that we have, those ones, some different things can happen. All right. Then the other thing that could happen with a limit at infinity is maybe we would have to use the squeeze theorem. So this one doesn't completely work the way we did it before because of this sine x. All right. So what we're going to do is we're going to use the squeeze theorem. All right. And we're going to start with the fact that sine x is always between 1 and negative 1. All right. That is just something that we should know, we should remember from trig. That's always true. And what I want to do is I'm going to build this function from here just using some algebra. So I'm going to add x squared plus 2x to both sides. So I'm going to x squared plus 2x minus 1. I apologize, to all three sides really. So x squared plus 2x plus sine x. And then x squared plus 2x plus 1. All right. And then, again, to get this exact function, I'm going to divide all three of these by 3x squared. So our function is always between these two functions. Now I'm going to take the limit of the two outside functions as x goes to infinity. And let's see if I can fit it in here. All right. And the way we're going to solve these is we could do what we did before, divide everything by x squared. Or if we remember kind of a quick rule, when the degrees of the numerator and the denominator are the same, we can just divide our leading coefficients. So this one gives me 1/3. And actually, to be correct, we're taking the limit of all three of these. To be 1/3 is less than or equal to this limit, which is less than or equal to this limit, it's also 1/3. Well, if the limit that we're trying to find is between 1/3 and 1/3, the only number that's between 1/3 and 1/3 is 1/3 itself. So that's a way to use the squeeze theorem. I wanted to review that as well as how you can apply that to limits at infinity. All right, let's move on to our last topic of Unit 1. That's the intermediate value theorem. So basically, what the intermediate value theorem says is that if we have a continuous function, all it's really saying is that it has to go through every point. All right, so you grow continuously. So if you were born at 20 inches, and you are currently, 63 inches, then at some point you must have been 37 inches. You didn't just skip over any heights, all right? You were every single height in between what you were born at to what you currently are, all right? So that's all the intermediate value theorem is saying, is that something must go through every point. And an example of a problem is, let's say we are trying to prove that this has a solution on the interval from 1 to 2. Now, a consequence or a corollary of the intermediate value theorem is something called the root location theorem. And a root is just finding the zeros, all right? So this is the intermediate value theorem, but more specifically, it's the root location theorem. So we're going to think of this as a function. So x to the 4th plus x minus 3. And the first thing I want to do is I want to find f of 1. So f of 1 is 1 plus 1 is 2, 2 minus 3 is -1. And then I want to find f of 2. Well, 2 to the 4th is 16, plus 2 is 18, minus 3 is 15. And I want to notice that this is a continuous function. And I know that because it lacks suspicious points or suspicious numbers, right? It's a polynomial. It doesn't have any denominators. It's not a piecewise function that's changing rules. There's no suspicious points, so it's a continuous function. And if it's a continuous function, that goes from negative to positive. So notice this sign change, all right? If it's continuous and it goes through every single point that could exist, it can't go from -1 to 15 without somewhere being 0, and it must have occurred on the interval from 1 to 2. All right, so that is how we can use the intermediate value theorem. Anytime they're going to try to have you find roots or show that a certain function takes on a specific value, you're going to use the intermediate value theorem. All right. That concludes our Unit 1 lecture. I hope that was helpful. Please check out our TikTok, where we're going to be putting out videos of solving problems that are related to Unit 1. And depending on when you're watching this, there's just going to be videos going from Unit 1 to Unit 10 on TikTok, on Instagram, on Facebook. Also, check out our Patreon, where we'll have some extras. Besides this video, there'll be some worksheets and PDFs of reviews. Again, for this limit, or if you're watching this in the future, then all of this exists for you. And you'll have access to Units 1 through 10, all the worksheets, all the TikToks, just like I mentioned, all right? So I hope you like this video and subscribe to our channel, and I hope this was all helpful.